actually, one of the simplest is ethanol. Now, in ethanol, one of the things that you have to pay attention to, the signal for OH in NMR can show up between 2 to 5 ppm. Now, this signal gets shifted depending on the concentration of the sample, but usually it's around 2 to 4. You would expect a 3-bond coupling. A 3-bond coupling with this CH2, and you would expect this to show as a triplet. But almost every single time you take the NMR of an alcohol, you actually see a singlet. The reason for that, the reason for that is because the solution that you do NMR in is CdCl3 and contains traces amount of acid. And that's how chloroform is actually synthesized. So when you have actually acid, you have an equilibrium. Usually acid is in water. And this equilibrium gives you CH3, CH2, OH2 plus. And this goes back and forth because of this exchange. You don't see the coupling or the spin-spin coupling of the OH. So OH shows up as a singlet. So when you look at your NMR, you should recognize that. In fact, I have already told you that you have an alcohol in the NMR section. So therefore, this would have a very simple pattern of a triplet and a quartet. Remember, a triplet and a quartet is the hallmark of an ethyl group. I'm going to go through the other groups as well. Now, the other time that you do not see a signal at all for OH, not even a singlet, is when you have deuterium exchange. If you happen, your NMR salt was D2O, that actually undergoes exchange to CH3, CH2OD, and HOD. And this doesn't show NMR signal, therefore you don't see even a signal for the alcohol. But I can assure you, in your exam, you have a signal, and that's going to be a singlet. Right? So let's not waste any time on this. Now, what about now that we're talking about alcohol, how many types of alcohol I can have? I can have a secondary alcohol or tertiary alcohol. A secondary alcohol, for example, something like this. So remember, you already know the triplet and the quartet. I talked about the ethyl group. Now, what about the isopropyl group? This group. This is an isopropyl group. All right? So that's going to show a signal which is very clear. It's going to be a septet. 6 plus 1. 3, 3, 6 plus 1. So that's going to be a septet. Okay? And a septet signal is a little complex, of course. It's the ratios of the signals are different, but you don't need to worry about it. But when you can look at it, you can see that. And these 6 hydrogens are equivalent, and they both show up as 6 hydrogens as a doublet. Okay? Because there are N plus 1. Negative 3-bond coupling is only 1 hydrogen. So an isopropyl group is a doublet and a septet, provided that there is nothing else there to couple it. Okay? There is nothing there else to couple it. So, for example, if I give you this, the NMR of this is very simple. This is an ether, right? So this is not going to have, first of all, that both sides of this are going to be equal, right? And it's going to have 6 hydrogen as a doublet and a hydrogen as a septet. That's it. The ratios in NMR, then you have to multiply by 2. Maybe the relative ratios are only shown. Yes? Why is it doublet? Well, N plus 1, 3-bond coupling. You have 6 hydrogens that are equivalent. So 6 plus 1 is 7. No, these six hydrogens are coupled with only 1 hydrogen. 1 plus 1? Okay. You got it? All right. The same way that you did the ethyl group, N plus 1 group. All right? But again, if I put now another hydrogen there, then things become very complex. So what would I see if I had something like propane? Remember, I interrupted the coupling there, so now I have actually hydrogen and hydrogen, right? What would I see the NMR for propane gas, for example? First of all, these 6 hydrogens are equivalent. The molecule has a symmetry, right? So 6 hydrogens should appear as a doublet. I'm sorry, triplet? Why triplet? N plus 1. 2 plus 1 is 3. 6 hydrogen as a triplet. For chemical shifts of these things, you can always use the table. But these 2 hydrogens would have to be 6 plus 1 would be a septet. Alright? So that would be 2 hydrogens. That would be a septet. Usually when we get to septet, you can see that we actually expand those for you in the NMR spectrum, but you can see the seven peaks, but the outer peaks are usually very small. So you get something like 4, 6. Actually, there is one other peak here. Something like that. So the outer peaks are even small. You can check some of this stuff that is in your book to see what the signal looks like. Okay?
Still got your bet on?
The other thing that we want to talk about is something like Cl, CH2. This is in your book. I have a whole bunch of these things not in your book. So what about something like this, right? First of all, the important thing is for you to figure out how many types of signals how many signals you're going to have. This CH2 and this CH2 are equivalent, right? So 4 hydrogen should be identical at the same place, the same chemical shift, right? In fact, I can write this for you. All right. So, and then you have the middle one that shows up at. So what this would be 4 plus 1 would be a quintet. You don't know what a quintet is? It's 5 bands, and this 4 hydrogens, 2 and 2, 4 hydrogens would be a triplet. In fact, the triplet shows up as 3.8 ppm, and this one shows at 2.2. And why is that, by the way? Because of the chlorine that is electronegative and pulls the electrons towards itself. And therefore, the chemical shift of these is moved in this direction. Okay, initially. Let's take a look at another spectrum. So what do we know so far? We know the ethyl group. We know the isopropyl group. What about a propyl group? Let's see if I have, a propyl group. That would be a good one to look at, right? Because you're basically in NMR, you get the original formula and you're trying to figure out by the number of multiplicity of the signals what kind of groups you have. And then you put them together for it to make sense. And of course, we use chemical physics as well as integrations to figure it out. So let's say I'm going to draw the structure of this compound for you, and I will discuss what you expect to see for the NMR of this. This is an ether. Because the molecule is symmetrical, how many types of signal do you expect? 3 types of signals. Which one would be the most deshielded? The most deshielded, less deshielded, definitely not very much deshielded. Alright, because as they go further away from oxygen, which is electronegative, the deshielding effect disappears, really. Okay, so let's take a look. The most deshielded one, which is this one, should appear at what kind of signal? Triplets, right? So this would be a triplet. And it actually shows up at about 3.2 something here. And then, what about the signal in the middle, the CH2? 3 plus 2 is 5, plus 1 should show up as a sextet, which means as a 6-band peak. Okay? Then you have this CH3, that will be a triplet, because it's only next to a CH2. This should be a triplet. And this is really not very D-shielded. That's why it shows up at around 1 dBm. Okay? So that's what is, yes. This one? Okay. So the first thing that you look at, we look at two things. We look at the chemical shifts. We also look at the multiplicity of the signals. When I have a triplet, a sextet, and a triplet, I must have a propyl group. But of course, you have to make sure you don't have you don't have this pattern, right? So for each group, that you have to figure out what combinations you're going to have. For an ethyl group, for example, we said that you have, guys, there's a lot of talking.